In this particular video, we are going to discuss about the jacketed CSTR, means continuously start tank reactor temperature control, and whether feedback control we need to use or whether cascade control we need to use, and what are the advantages and disadvantages for the both. So this is a typical jacketed CSTR control scheme. Here we are considering a simple feedback loop. So let's discuss about the process first maybe. So this is the feed that is going into the reactor, and this is the product that is coming out of the reactor. And this reaction that is taking place is an exothermic reaction, and the temperature is increasing as the reaction is happening. And we need to fix the temperature to a certain level for the optimization in the reaction, and so that we get the desired product. So basically our temperature within the reactor needs to be maintained, right? And how we can maintain that reactor temperature? This can be through a coolant, right? This is some coolant is going, and this is keeping this as a jacket and cooling the reactor, right? So this is how the temperature can be controlled. Now for this particular case, there is a measurement, temperature measurement from the reactor, inside of the reactor. It is measuring the temperature and feeding it to a temperature controller. Operator gives a set point, say operator gives a set point of 300 degrees centigrade to it, and then the output of the controller goes to the valve, and the valve modulates, or valve open or closes based on this MV value. And as the valve opens or closes more, this coolant flow will increase or decrease. And depending on this coolant flow, this temperature of the reactor is maintained. So this is a simple feedback control loop. Now, what is the problem associated with this loop? Now, there are three problems are there. One is, or three disturbance sources are there. One of the source is obviously this coolant temperature. The temperature of the coolant that is going here, whether it is constant or it is varying over the time, or varying with respect to some process disturbance in the upstream of this valve, right? So there can be any issues for this. This coolant temperature can vary over the period of the time. And if the coolant temperature varies, right? So the coolant temperature varies, so this control mechanism will not be able to detect that variation quickly. It will ultimately detect, because if the coolant temperature goes down or goes up, goes up, coolant temperature goes up, then it will not be able to effectively cool the reactor, and it will increase this temperature, and then again this controller will act. But there will be a sufficient time delay in this process, right? And because temperature is obviously a slow process, and increasing the temperature will take some time. But what you will lose here is, you will see the temperature rising, and it will lead to an disturbed condition, or not a, and it may also impact in your product. So it may cause the product to be off spec or something else, right? And if the disturbance is such that it is temperature is increasing and again the temperature is decreasing, then it is very difficult to control, because by the time this temperature, so, so suppose this coolant temperature increases, right? And by the time this particular temperature increases, this again goes down. So there will be a sufficient delay in this control action, and it will never will be able to control this temperature. So that's why conventional feedback mechanism is sometimes avoided if there is sufficient disturbances can be considered uh, from this coolant flow, right? And similar thing also may happen with the feed. Feed temperature also may vary over period of the time, and that may also cause the disturbance in the or unstable the process, right? So let's look how we can avoid the disturbance caused by the coolant temperature variation. That's, that can be achieved through cascade control. For that, we need to have another temperature instrument, and that will detect the coolant temperature, and there will be another controller here, right? So this TT1 will measure the temperature inside the reactor and will give the PV value to TC1 or first controller. TC1 will get set point from the operator, and it will generate an MB. Now this particular MB will act as SP, set point, to this temperature controller. And to this temperature controller, PV will come from the second temperature instrument that measures that coolant temperature, right? So whenever there is and this will generate an MB, and this MB will go to the one. So whenever there is a disturbance in the coolant temperature, TT2 will detect that temperature variation, and it will send that information to TC2. Now TC2, based on the SP it is receiving from the TC1, it will adjust this output. So if your SP is constant, because suppose this TT1 is showing a constant value, so this SP will be a constant value. But your PV is varying. So if the PV is varying, that's why the MV will vary. And it will adjust the flow accordingly so that your TT1 temperature can remain constant. Right? So this is how it can be achieved. The disadvantage of this particular process may be you need another temperature element here to achieve this control, and also you need to tune the loop properly. Without properly tuning the loop, it does not make any sense to use the cascade control. So that can be another disadvantage, but obviously you will achieve much more optimum control, and that control will give you more revenue, because you will always get proper product. The chances of obsolete products are reduced, right? So in that sense, adding that extra instrument and adding that extra complexity to the system may be justified.